Okay, so we'll talk about basic antenna parameters, which a little bit about the E-plane patterns, not much about H. Gain again as a function of the radiation pattern and antenna modeling with things like EasyNet. I don't know if people are familiar with EasyNet. It's a antenna modeling tool that was developed by Lawrence Livermore Labs, as well, a guy that worked there. They have an old Fortran program called NEC, which was network. Oh gosh, I forgot now. It was a way to calculate electric fields. And this guy, I can't remember his name, came up with this interface for it that lets you use it instead of having to write Fortran, and you just kind of model the segments and stuff, and you can find out what the SWR is and the radiation pattern and all those kind of things. It's kind of neat. It takes a little learning curve. So directional antennas are said to have gain. We talked about it's not really gain, although you get more power in one direction than in another. So it's a relative measure. Um, and the total uh, power out is less than or equal to power in. So one of the things they do to come up with these patterns for an antenna is actually go measure the field strength at various points and plot it. And you'll see these kind of charts. This is like a typical, probably a Yagi. It could be a quad, but it's definitely a beam antenna. So you have this major lobe that's out here in one direction, and then you have some minor side lobes, and you have a minor back lobe. And this is in the azimuth plane or horizontal. So that's why they call it azimuthal radiation pattern. And they reference the peak point as 0, and then they come back in negative dB. So if you want to look at the difference between the peak forward and the peak back, then you can look on here where it crosses probably what's halfway between 12 and 24? 18. So it'd probably be a 18 dB front to back ratio in that case. And these patterns are done in what they call the far field. When you're up close to an antenna, you can't really measure the pattern. There's just too much stuff going on. So you have to get to a point far enough away where the pattern is consistent and doesn't change with distance. So regardless of how far I am from the antenna, I'm going to see this same shape pattern. Now, the power level on the surface of that pattern is going to decrease as the pattern gets bigger because I only have so much power coming in, so I get so many milliwatts per square centimeter on the pattern surface. How'd I get that up there? So what's the difference in radiated power between a lossless antenna with gain and an isotropic radiator driven by the same power? Yep. Radiated power is the same, doesn't matter. What's the far field of an antenna? Okay. What's the title on this thing? Oh, beam width. So if we look at the beam, what we call the beam width, we look at the 3 dB, the half power points or 3 dB down points. So you can see over here where I put the arrow, this minus 3 dB line, where the pattern crosses it, whatever that angle is, you double it, and that's the beam width. So in this case, it's what, about 50 degrees, 25 and 25, more or less. So what's the 3 dB beam width of an antenna radiation pattern shown in figure 3 or E91? Looks familiar.
Remember, still working.
Okay, front to back ratio. It's a measure of how directional the antenna is. So like I said, you look at the difference between the main lobe, which is the maximum point is 0, and the back lobe. And on this one, it's the same chart as before. It's 18 dB. So that's the front to back ratio. And this one looks familiar too. So what's the front to back ratio of that pattern? Yeah, so you think that's 18? Yeah.
Doesn't look like 18 to me, but does it?
Well, this is 24 and this is 12. So it's about halfway between 12 and 24, even though the scale is not really linear.
It's logarithmic, no.
Right,
But that's as close as we got.
right. And the only other close one is 14. This is one of those where
Closer to that.
okay, front to side ratio, same kind of thing, except we're going to look where the front is relative to the side lobes. And in this case, it's a very symmetrical pattern. It's not necessarily true if there's anything interfering with it. You could have a left side lobe bigger than a right side lobe. But here again, we have to interpolate, and it's a little more than 12. I don't know, I'd believe 14 in that case.
It's no sense to me, but that is an answer on the other question where we're from.
So guess what this question is?
Actually, well, I have to go with Delta. I've noticed a trend there.
Oops. Okay. We also need to see how it performs vertically. All those were the horizontal pattern. The elevation pattern or vertical, and we see lobes coming up in this case because it's a beam antenna, and that's one of the effects is you start getting extra lobes. You wouldn't see that if it was a dipole, and we just have 2 lower lobes when we look at the cross section. In this case, you try to find the angle of the major lobe, okay, which is the lowest one. And since these are 15-degree lines, then that's about 7.5 degrees. So can we guess what this question is?
No, because that black box is there. I'm cheating, you know.
What's the elevation angle of peak response in the antenna radiation pattern? what's the front to back ratio of this vertical pattern? You do it the same way. So your front is 0 and the back is down here, what, a little less than 30?
So wait a minute, the key, what are you doing here? What's the?
Front to back. Okay, this is the back lobe, the maximum back lobe. Okay, it's a little less than minus 30. They're saying 28. I'd go with that. So none of the others are close enough. Okay, modeling. Like I mentioned, one of the most popular ones is called Easy Neck. There's a couple other variations that people have done improving on the interface. There's one Simple Neck or something like that, which lets you do it graphically. In Easy Neck, you have to do it and put numbers in for the number of segments that you want and the location of the endpoints of the wires. So it's a little tedious to actually model an antenna. Fortunately, they have a library where they've done a lot of them, and you can pick from one of those and make some changes easily. You can get SWR versus frequency from the model. You can do polar plots for azimuth elevation. You can get a 3D radiation model that you can rotate around and see what the pattern looks like. It'll show you the complex impedance values at any frequency you pick. You've got a marker you can move around on the plot. And one thing they all use, because they're basically all based on the neck analyzer. Wish I could remember the name of it. Something. They use what's called method of moments. So you divide all of the elements of the antenna up into segments, and they calculate for each segment what the current is and what the radiation pattern and all those things on a segment by segment basis. So the more segments you have per length of element, the more accurate it's going to be. You have to have at least 10 times the segments per wavelength, I think it is. I think it's on the next chart. The downside of having too many is, depending on your computer, it can take a while, particularly if you're doing it over a wide frequency range. But if you don't have enough, I mean, you can get really weird answers. So it has some warning things in there, and it'll tell you that, your segments are too big, for instance. So what type of analysis is commonly used for modeling antennas? What's the principle of method of moment analysis? Is it? Mhm. It calculates the voltage, but it's based on what it figures the current is in each segment. Let's try alpha.
Then this is all about current.
I was getting around to it.
They figure a uniform current per segment.
I missed you saying that.
Okay. I think I did, but I may not
I
have.
probably did, I just missed.
I can't remember what I said. It's been too long. What is the disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength? Very good. Okay, so radiation patterns are just plots of the field strength out in the far field. Far field is the region where the radiation pattern doesn't change with distance. See, the power into the antenna is the same regardless of the pattern. The 100 watts in, maybe 100 watts out. The beam width is the 3 dB points of the main lobe and whatever that angle, those two angles are. Because again, it doesn't always have to be symmetrical. You could have a weird shaped lobe.
If it's not symmetrical, then it won't be times two.
You just add them.
You just have to look at the two.
Right.
points.
The front to back ratio is how directional it is, which is just the difference between the rear, the dB level of the rear lobe versus the front forward lobe. And usually the maximum lobe is plotted as 0 dB as your reference point, and everything's relative to that. Front to side's the same way. You're doing the front to a side lobe as opposed to a rear lobe. An elevation pattern is just the field strength cross section in a vertical direction. The maximum vertical lobe is the elevation angle, whatever the peak of that is when you measure that angle. And it'll normally be the lowest lobe in the pattern. And then you can also have front to back vertically as well as horizontally. Modeling programs like EasyNet use method of moments, and you need at least 10 segments per half wavelength.